use maybe one of the wet or the dry season for calibration and then the other season for validation. We call this differential split approach. So it will take us much time to discuss all. So I would like you to go through calibration, validation, and also there are some very helpful notes here. Okay, for example, if you see that Apex predicts surface runoff high and phase flow high, and evapotranspiration is small as compared to original estimate, you can see the rate is simulated and the one here is observed value. It captures the trend, but it, uh, it overestimates, right? Both phase flow and surface runoff. And now these are the options, suggested options in your calibration. This is, you need to know your model process very well. So if this is happening, you can decrease the curve number by decreasing the land use number. Remember in the operation file how to change the land use number. If you minimize the land use number, it's going to force the curve number to be reduced. Okay? So if you change this land use number in OPV2 of the operation file, then it's going to reduce the surface, the flow. And also change the parameters which are associated with direct runoff. And which are those parameters that have listed them here. Increase the soil moisture storage capacity so that the model infiltrates more water. Okay? And then this will mimic the observed value. Parameters which are associated with soil moisture storage capacity is in the soil file. The soil file about bulk density, fill capacity, wilting point, and bulk density. And increase ET parameters. As I said before, this depends on the type of ET estimation. So you might check parameter search for if you use Hargreaves method. This is for Hargreaves method. And the others you can see if you have a manual. You can also increase recharge so that the stream flow decreases. That is the conceptual way of doing calibration. So most of the time when you are doing modeling, we don't rely on automatic calibration. So automatic calibration, it captures random sampling, and the same parameter values might give you different output. Okay, because it's random sampling, or different parameter values might give you the same result. And you need to know the process, and also you need to know how to adjust the manually. And this is also a suggestion if you have such type of flow. Okay, predicting and overestimating the peak but underestimating the base flow. So there are different combinations, and these are the suggestions how you manage it. And this is problem with sediment data. Most of the time, sediment data is very hard, okay, to calculate, but you need to check the hydrologic properties of your catchment, like area, slope length. Also check the saturated conductivity and erosion control factor in the set area 5. And also check the water erosion method, how you compute the water erosion. That is DRD parameter which is controlling this. And adjust also the threshold value for estimating erosion. For example, if the threshold is high, that means it means you will not be estimating sediment until it reaches to the threshold value. So if your estimation of sediment is low, then you minimize the threshold value to generate sediment. This is the rainfall erosivity. And this is for crop yield calibration. So in the crop yield, as I informed you earlier, first we need to check our water balance is in a good condition. Okay, so we start from water balance component, and then you check for a stress condition. If there is water stress, if there is nutrient stress. Okay, most of the time we might underestimate the prediction of crop yield. If that is the case, we check the water stress and nitrogen stress level and revise the parameters associated with water and nitrogen budget. Aeration stress is if the field uh, is not aerated, for example, if it's flooded, you might have aeration stress. And temperature stress, if there is high temperature stress that we saw this morning, also check this optimal and base temperature in the crop file. Aluminum stress is uh, for lime application. So if you have aluminum stress, also check this. Salt stress, so that's associated with electric conductivity in the soil. And check also the salt in the amount of irrigation water. So this is without modifying any crop parameter. So we would like to stick with the crop parameter and just modify the water budget, nutrient budget, and others. Only these are the crop parameters, for example, in this case. And also, if you like to go more, you can see the harvest index, as I told you earlier, and also the germination factor, seed germination factor. And here is also those development curve. These are the parameters in the crop. Also root development factor. These are parameters in the crop. The root development factor, if for example that's minimum, is not allowing the root to grow, that might lead to reduced yield. So these are some of the parameters that we have been working on related to flow sediment, and also this can be associated with crop because modifying those values will lead to crop yield modification. So this is all about the calibration process. It's also available here uh, in your PowerPoint. So similarly, I want you to go through all this PowerPoint from day 1 to day 5. There are conceptual things here, and I want you to check everything in this folder. Besides the manuals, actually, so the manuals are also available here. If you are working on the Apex, you need to master every manual here, and you need to read all here from the manual and also the PowerPoint. Good so far? So for example, now you have this sensitive parameters. So let's say we ignore parameter 42, SATO, and let's ignore this only the two parameters. So in the Apex Qt folder, in the projects, we go to the parameter calibration again.